Well, I have a new piece of gear to review from F-NIRSI. This is the LC1020E high precision LCR meter. It lets you measure inductance, capacitance, and resistance or impedance with high precision. And it has a special probe for that, which I have never talked about. Actually, something fairly new to me, but I've done some research on it, and we'll look at it. So let's take a look at the F-NIRSI LC1020E over here on the bench. Let's open this up, see what comes in the box, and put it through its paces. Here's the box. On the back, we have all the specifications. I will put a link in the video, of course, to the site for the meter if you want to go and peruse those more specifically. But we do have several frequencies from 100 Hertz up to 100 kilohertz. And it's good that it goes down to 100 Hertz. You want a very low frequency if you're testing capacitance, especially if you're going to try to test a quality of a capacitor in circuit, which is possible to do because this will also operate at a very low voltage from 0.1 to 0.6 volts. Meaning that if you try to test a capacitor in circuit, the voltage is low enough not to trigger a solid-state device. Of course, you do have to consider other resistances that might be in the circuit. But in a lot of cases, you'll be able to actually tell if a capacitor is good or not without desoldering it, which is really nice. So anyway, all the specs are here on the back. Let's open up the box and see what's inside. No fancy carrying case, I guess, just the meter this time. All wrapped up and protected. Some diagrams of the different included test leads. Okay, we've got a standard set of probes. Pointy, no caps, just pointy probes, a USB charging cable, and oh, there's something else in there too. Oh yeah, a little user's guide. Looks like it's 2 languages. Yeah, Chinese and English. Just a quick operations guide. Breakdown of the buttons with a description of each. And some basic information on operating. And a warranty card. And then I want to look at what's in here. Have you ever seen probes like that? Some of you have, I'm sure. You can see there are 2 wires to each clip lead, and we've got these big clips here. They've got serrated teeth on them so they'll get a good grip. And this plug that plugs into the meter, and it says Kelvin clip. These are Kelvin probes. What are Kelvin probes? Well, let's talk about that first. So let's first consider a standard 2-wire multimeter measuring resistance. You may be surprised, or maybe you've already realized this, but the way it works, the meter actually measures current and then calculates the resistance. So the way it works inside the meter generally, this is just an approximation, simplification, but the meter has a voltage source over here, and it knows the value of that voltage, and it's feeding through a shunt resistor that has a very precise value, and then the current goes out through your test resistor and comes back. So the meter measures the current by measuring the voltage drop across its known resistance, and it knows the voltage that it's feeding and then uses those values to calculate this resistance, this unknown resistance. The problem is the wires themselves, these test leads, have resistance, and anytime you have current flow across the resistor, you have a voltage drop. So the test leads themselves are going to skew the measurement slightly. In most cases, that doesn't matter so much. You know, if you're just a hobbyist, just checking a resistor value, the small amount of difference is not going to matter. But if you want to use a very high precision to make measurements, then this resistance of the test leads makes a difference. So in the 4-wire system, it works a little bit differently. The meter still sends a voltage and current out on 2 of the wires, these feed wires here, and they cause a voltage drop across the resistor. The difference is there is a second set of wires that come out and connect across the resistor. And this input on this second set of wires is a very high impedance, multi-mega ohms. So there's not going to be any current flow on those wires. All it is doing is reading the voltage across that resistor or test component. And since there is no current flow across those wires, there's no skew to the measurement. That's the way a 4-wire system works, to give you a very high precision reading. And that is the Kelvin probe. Well, let's have a look at the unit now. So it's fairly light. It has a built-in stand for putting it on the desk. Nothing really around the sides aside from, over here, a USB-C. Yes, USB-C charge port and a small hole for a reset button, I think. You can also use this to upgrade the firmware. No storage capability, though. On the front, we've got a nice big color screen and our interface buttons and our inputs down here. Fairly easy, fairly straightforward. Let's power it up. Little animation. And we drop right into capacitance measurement. So, the input buttons. As you can see on the screen, there are 2 simultaneous measurements. It gives us information here about the current testing frequency, the current amplitude of the test signal, DC bias offset, and our range, which is presently set to auto. We have 2 measurements. This first one is now set to capacitance, and the second one is set to D for dissipation factor. Our options are, for the first one, capacitance, inductance, impedance, and resistance. On the secondary, we have X, which is reactance, D for dissipation factor, Q for quality factor, phase angle, and ESR, equivalent series resistance, for testing capacitors, determining their quality or age. We also have navigation buttons here. An OK button that takes you into the menu system if you hold it down. So in the menu, we have language, brightness, volume, timeout timer, calibration, which is on the second page. I would think that should be on the first page. That's probably something you'll access more than you'll access the other things. And system, which lets you see the version. Presently, I've got it at 1.1. I've updated it. It came with 1.0. And there is a restore button in here for restoring factory defaults. To get back out of a menu, you just hold down the OK button again. And that takes you back a level. Down here we have a hold button to freeze our reading. Speed is how quickly it's doing its measurements. Range is, well, for the range of whatever you're in. Right now we're in resistance. If I hit the range button, now we've got 100 ohm resistance range, 1K, 10K, 100K, and auto. Frequency is the testing frequency. Now this meter, as most LCR meters do, sends out a AC signal through the device that's being tested. And there are several frequencies that you can choose here for that signal. From 100 hertz up through, I think, 100 kilohertz. Right now it's at 1 kilohertz. And you want to set that based on the device you're testing. Now here is a reference that I found. Many LCR meters will have a reference in their manual. This one does not, but I was able to find it online. And it's just sort of a basic rule of thumb. Small capacitors, less than 1,000 picofarads to up to less than or equal to 10 nanofarads. 1 kilohertz or 1 megahertz. You probably want to go above 1 kilohertz for these really small capacitors. Medium capacitance, which is where you'll be most of the time, 10 nanofarads to up to about 10 microfarads, 1 kilohertz, which is the default. And if you get into large capacitors, greater than 10 microfarads to hundreds of microfarads, then you'd want to go down to the 100 hertz or 120 hertz frequency. And the exception being high frequency RF capacitors, ceramics, small film, and so in RF circuits, 1 megahertz or higher. You're probably going to be in 1 kilohertz for most capacitors you're testing, but you know this reference range is sort of a rule of thumb. Smaller capacitors, higher in frequency. Larger capacitors, lower in frequency. Same thing for inductors. Large inductors, you go lower in frequency. Small inductors, you go higher in frequency to get an accurate reading. And that is that on the interface. Down here we have our inputs. Now the Kelvin probes have this fixture that goes in here. You just insert that like so, and then push it over to lock it in. And you're ready to make measurements with your probes. Let's measure a couple of capacitors just to see how well it works. So I have a box of miscellaneous capacitors. A lot of these came out of old Heathkit kits way back in the 1970s or so. So some of these are quite old, and that'll give us an interesting test to see how well they hold up. I'm just going to pull a few random ones out of here. Now, I'm going to leave it at 1 kilohertz. Let's see what this capacitor is here. Now, this is 100 microfarads, so we want to go down in frequency. So we'll go down to 120 hertz for this one. So this is a 100 microfarad cap. Polarity isn't all that important because we're using a very low voltage, but I'll follow polarity here. Negative to negative, positive to positive. And we're seeing 104 microfarads, which is respectable for this old of a capacitor, and an ESR of 0.82 ohms. Now, ESR, equivalent series resistance, as an electrolytic capacitor ages, it begins to develop, or higher resistance actually, to AC current. A capacitor, a perfect capacitor, should be 0 ohms to AC. It should pass AC completely through it within its frequency band or range. But as a capacitor ages, it'll develop a resistance, and if it's a filter capacitor and a power supply, it can become a load. So if that ESR is high, it's an indicator that the capacitor is getting old. But what about that ESR value? Well, there's no real solid guideline for ESR. It varies on the manufacturers of the capacitors. Most manufacturers will have data sheets on their capacitors, and you can look up what the ESR should be. That's the most reliable way to find out if your capacitor is good, using what the manufacturer recommends. But here is just a general guideline on ESR values. And you might want to screenshot this. I'll put it as big on the screen as I can so you can screenshot it if you want to save it. But it gives you a rough idea on capacitor value and quality reading for the ESR. So for 100 ohm, very high quality, we should see as low as 0.069. High quality, we should see 0.173 ohms. Normal is around 0.24. Low, very low is up 0.875, and we're seeing 0.84 ESR with this capacitor. So this is beginning to present a DC or a resistive load, and would probably not be a good choice for a filter capacitor and a power supply because it would load down the rail that it's supposed to be filtering. So, and it's quite old. Like I said, this is probably from the 1970s, so that's not unexpected. I'm going to go ahead and toss this capacitor. I'm not going to try to use it in anything because that could give me trouble in what I might use it in. So this is where an LCR meter, it can be pretty handy for testing your components. What do we have here? 51 plus or minus 3%, 500 volts. So this is a low value. We probably want to go higher in frequency. Let's measure it at 1 kilohertz and see what we see. Okay. 54 picofarad. We're actually reading it okay at 1 kilohertz. What was that frequency, suggested frequency range? We should go higher in frequency. Let's see if our reading changes. 10 kilohertz, we're reading 52.5. According to our frequency guide, we should be at a higher frequency. So it's rated 51, we're reading 52.5. That's fine. Of course, these guys don't age very much. So yeah, handy for checking out your capacitors. The other thing you can measure is inductors. I have one I wound here on a type 2 core. This should be really low in inductance. It's not that many turns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 turns. So I'm going to switch to inductance and quality factor. And it's a low inductor. I probably need to go a little higher in frequency. 0.9 microhenries. 10 kilohertz, I'm reading 0.8 microhenries and a 5.3 quality factor. 100 kilohertz, I'm still reading 0.8. So yeah, small inductance, we wanted to go higher. And 10 and 100 kilohertz, both, I'm reading at 0.8 microhenries. So that would be handy if you were winding coils and you wanted to make sure that your values were exactly right.
Okay, so what about accuracy on this meter? I'm going to make some measurements with a calibration board that I have, but first I wanted to talk about price. If we go and look at the Amazon page, we see that this meter sells for about $80. And that is, well, that is in the affordable range. That's a fairly low price for LCR meters. If we go and look at a name brand, a quality name brand like BK Precision, we see that an LCR meter is going to run you over $500. So how are they getting away with only $80? Well, I'm going to guess that we're probably going to see that it's not very good on accuracy, but maybe they'll surprise me. So let's go and take a look at accuracy. I did do a full calibration on the meter before I started making these measurements, by the way.
Okay, I have a precision reference board here that I bought a while back. It has capacitors and resistors, and these were measured at the factory on high quality equipment with the absolute values written in. And so we can then make a measurement on this meter to see how precise it is. So this first capacitor up here should be 97 picofarads. I am going to put the probes on it, and we'll see what we read. 97.4. All right. Okay, this one should be 104 nanofarads. I'm reading 101.1. Well, that's nanofarads. Let's go up in frequency. 106. 1.04 microfarads. And I'm reading 0.9, so we're just a tiny bit off. Let's read resistance and look at the precision resistors. This should be 10 ohms. 9.995, that's pretty good. This should be 100.06. 100.04, so that's pretty good. This should be, I think that says 8.999K. Okay, maybe that's, oh, that's a 0.999. Okay, yeah, that's right. Whoever did this, their handwriting is terrible. This should be 100.02 K ohm. I think that's a 2, 100.0. Maybe that's a 4. Let's read it. There we go. 100.05. So it's reading very, very close on the resistors, almost dead on with this little calibration board. But we're getting a slight error on capacitance. And I know I've calibrated the meter. So, I don't know. As with anything else, it's a brand new product. There may be improvements with firmware updates, and it might be okay as it is. It certainly is going to give you more accuracy than your run-of-the-mill cheap capacitance tester or cheap multimeter.
As I mentioned, I don't have other more accurate meters to compare it against, but I checked with my friend Kerry Wong. He does a YouTube channel where he looks at test equipment, and he has actually recently reviewed this particular meter, as you can see here, and he did compare it to other meters. So I contacted him, and he let me know that he also observed poor accuracy on the F-NIRSI. And if you're interested in looking at his video, I will put a link to it in the description below so you can go and watch him compare this meter to other meters. Well, as the saying goes, you get what you pay for. And at only $79, a fraction of the price of big-name meters, I don't expect it to compete with them. However, it's certainly much better than your cheap capacitor meters or multimeters, and I think it's actually overall a good bargain for the hobby market. In the video description will be a link to their Amazon page and information on a discount code that will get you a little bit extra off if you decide to purchase this meter.
Well, there you go. The F-NIRSI LC1020E LCR meter. I hope you found that interesting, and as always, links are in the description below. We'll see you in the next video.
Thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.